Okay, so the plan for this week now is you'll have a live lesson today, a live lesson Thursday, your assignment then on Friday. It may take another live lesson to do the whole of the topic, though, so we'll have to just wait and see how that goes. Okay, so a bit flexible, but that's hopefully what the plan will be. As you've probably seen in the news, we're going to be back in school potentially from the 15th of March. So that'd be good. By that point, we might well have pretty much finished the course, or we might be there or thereabouts to be on the last topic or so. I think we'd both like to go through some of the topics that we've done during lockdown again, because just to cement that knowledge. But we're starting the most difficult topic left today. All right, so that is integration by substitution. There's the title, integration by substitution. Now, today's lesson is difficult, but the next one is more difficult. Okay, so you really need to make sure you get a grips of, I would say the word basic stuff, but it's not basic, in relative terms, it's easier than the next lesson. So I want you to make sure that you really understand what I'm doing today before going on to the next lesson. So if it takes another watch of the video, takes another read of the notes, ask us questions or whatever, that's absolutely fine, because it is a difficult thing to get your head around sometimes. Okay, so integration by substitution. These are the notes Mr. Stratford has on the classroom. I thought today I'd keep it consistent and I'd use his notes and just talk you through them. All right, a bit more of an extra explanation as we go along. So essentially, in its most basic terms and most basic description, it is the reverse process of the chain rule, which is differentiation. Now, we haven't done chain rule in a while, so it starts off by saying, you haven't done chain rule in a while, but there's a bit of an example to show you what it means. But right here, this part here, that's the chain rule in its most basic term. dy by dx is equal to dy by du times du by dx. So we're just talking differentiation now. We haven't reached the integration stage yet. That's just a recap. We did this earlier in the year, and it's when you have to substitute something u in for something particularly difficult in the original equation, and when we substitute u in, we have to find dy by du and du by dx, two separate things, multiply together to find dy by dx. So this example, we're given a question here. It says, if y is equal to e to the power of x squared plus 5x, find dy by dx. So differentiate that. Now, we may well know the quick method. Now, the quick method is we multiply the integration, we multiply by the differentiation of the power. Okay, so, but that's just one of the generic rules that goes with the chain rule. It stems from the chain rule. And the chain rule would be to substitute something in for the difficult part. Now, in this case, the power is the difficult part. So I'm going to let u equal the power of x squared plus 5x. Now, remember, the chain rule is this thing here. So I need to find a couple of things. I need to find dy by du and du by dx. So what I need to get is equation y involving u and an equation u involving x. Now I have now, with my substitution, an equation of u involving x. U is equal to x squared plus 5x. That's my power up there. But I also need another equation of y involving u. Essentially, what was my original equation, but with u substituted in? Well, it was y equals e to the u, because u was my substitution for the power. So I need those two things. And if I differentiate those two things, I end up with du by dx, because I'm differentiating u with respect to x. And I end up with dy by du, because I'm differentiating y with respect to u. So differentiating those two is nice and easy. 2x plus 5. E to the u, e to anything, stays the same. So the chain rule is dy by du times du by dx, just multiplying those two things here by each other. There is one slight difference, though. I need to substitute my u, whatever I had for my value of u, back in, which was x squared plus 5x. And if I chuck all that back in, I end up with du by dx times by dy by du, just with the u sub back in. And that's the answer. That's the answer to this differentiated. Now, we know there's a potentially quicker method now where we just differentiate the power, which is 2x plus 5, and just chuck it in front to give me this. But this is where it stems from. The chain rule is where it stems from. So moving down to this part here. So I did mention at the start of this lesson that integration by substitution is essentially the reverse process to differentiation using the chain rule to a certain extent. So if I have and this was my answer, this part here, 2x plus 5 brackets e to the x squared plus 5x. This is my answer. I know that if I integrated that, I end up with this here, because that was the reverse of what I just did. We just don't know how to do that. If we were given this as a question with the brackets 2x plus 5 e to the x squared plus 5x, I wouldn't know yet, or you won't know yet, how to get back to this, how to integrate this to end up with that. We don't know yet. But that's what integration by substitution is all about. Okay, so this part is important, this sentence here. It says, when we need to differentiate using substitution, the substitution is usually given in the question. Now, when we are doing the chain rule, you can choose a substitution yourself. You become something, and it's usually quite obvious because it's just a difficult thing. However, when it is integration, the substitution is not always obvious. Now, I think it's about 90% of the time they tell you exactly what to substitute in this question. We'll see in a moment. It says to use the substitution u equals x squared plus 5x. However, there are some occasions where they don't, and you have to choose a substitution for yourself. That, I think, when we get onto that, is the single most difficult thing you'll do this year. Okay, so if they give us the substitution, good news. If they don't, bad news. So here's the question. Example one. Essentially, this is the reverse process of the previous question. But I'm going to get rid of the previous question. Just imagine that this is a new question. Okay, so find the integral of this thing here. 2x plus 5 times e to the x squared plus 5x. So you might be thinking, why can't I use integration by parts for this? Because there's two things multiplied together. Well, I'd say the power is far too difficult to end up with something that will easily cancel out for that one. But they tell us to use the substitution. So there's the method, integration by substitution. And they tell us exactly what they want us to substitute in, which is good news. This is one where they've told us that we want the substitution u equals x squared plus 5x, a bit in the power. So step one, we need to differentiate the substitution in terms of x, then rearrange to make dx the subject. Now, at this stage, it's not going to appear incredibly obvious why we do that. But when we substitute back into the integral, it will, I think, make a bit more sense. So they've told us to use the substitution u equals this. So I'm going to use that. And the step one is to differentiate it, du by dx. And we end up with 2x plus 5. Because that's the easy differentiation of x squared plus 5x. But then it also says our step one is to rearrange it so we get dx on its own. Now, dx is on the bottom of, or you could think of it like on the bottom of the fraction, not that it's necessarily like that, okay? And it will just swap sides with the 2x plus 5. So if I want to get dx on its own, the 2x plus 5 gets swapped underneath, and I have this thing here, which is important. Along with this thing here. Those two things are really important. My substitution they give us in the question, and my rearrangement to find dx on its own. So those two things are really important. They are listed now in this step here. The two important things I mentioned on the previous part. So if I substitute those two important things, the substitution of u and the dx on its own, I can put them into my original question. If I scroll back up to have a look at the original question, okay, I have this thing here. Okay, now there's certain parts of this I can replace with u's and dx's and what have you. So this part on the left-hand side of the equals here is my original question. But what I'm going to do is I'm going to substitute these two things in, hence integration by substitution. So in the power, x squared plus 5x, that was u. So that gets replaced with e to the u instead of e to the x squared plus 5x. The other thing that gets replaced is the dx on the end, because now it's not really going to be with respect to x anymore. It's going to be with respect to u. So remember in this previous part, I rearranged my differentiation to get dx on its own. So instead of dx, I'm going to replace that with du over 2x plus 5. So essentially that is substituted to give me that, and that is substituted there in the power. So it wants me to simplify all of this now. Okay, so again, the left-hand side is what the question was in the first place. But I can simplify this on the right-hand side here because 2x plus 5 is on the top and the bottom. So they will cancel out. And I am left with the integral of EU du. So to work out this long, complicated-looking question I had in the first place, it's actually just a case of integrating e to the power of u with respect to u. Now, if you integrate e to the u, it's the same thing. But just to finish my question, I need to replace the u in the power with my substitution I had in the first place. So the final answer of integrating e to the u is e to the u, but I replaced the u with the x squared plus 5x that I had in the first place. But don't forget that we have a plus c as well. Okay, so those are the steps that you need to take for integration by substitution. So just going to work through those steps again. I'm not going to do the whole question, just to remind you what we need to do. If a question looks like this and it says use the substitution, then good news, because they've told us exactly what we need to substitute in. In this case, it is u equals x squared plus 5x. So your steps are these. Differentiate it, then rearrange it to get dx on its own. You will end up with two important things then, the substitution they told you in the question and your dx on its own. Those two things get put into place into its original question. Hopefully, something should cancel out and make your integration a lot simpler, like e to the u. If it doesn't, if nothing cancels out and nothing simplifies, chances are you've done something wrong. Now, obviously, when you are told a substitution, it should work. If you have to choose the substitution yourself, that's a completely different ballgame, but we're not going to do that today. Okay, on to some other examples underneath here. Okay, so first one, another difficult looking integration question, but the clue will most of the time, or if not all the time, be in the question. It's going to either tell you the substitution, or it's going to say by using a method of substitution. So we don't mix it up with integration by parts or any other type of question. So this one wants me to find the integral of x times 1 over the square root of 2 plus x squared dx. This is my substitution they want me to use. U equals 2 plus x squared. Now, hopefully, if I choose my method correctly and follow the correct steps, something will cancel out and it will give me a lot easier simplification, and something will cancel out and a lot easier integral to work out later on. So my steps were differentiate u. Differentiate this. You get 2x because 2 goes to nothing. 2 goes in front of the x. You have 2x. Rearrange to get dx equals. So if I have du by dx is equal to 2x, they swap places and you get dx equals du over 2x. Now, excuse my handwriting, I want to sub u and dx in. Now, in my original question, that was up here, x times 1 over this square root here, which is now down here. I want to substitute in this, and I want to substitute in this. wherever possible. So 2 plus x squared was the bit underneath the square root. So that becomes a u underneath there. Dx is going to be replaced by du by 2x, or du over 2x. So you end up with this here. Now it's x times 1 over the square root of u, du over 2x. Now, this still looks quite complicated. However, there's usually something that will cancel out. There's an x on the top, there's an x on the bottom. So essentially, well, if I write this a little bit differently over here, just to show where all of this comes from, this is what we currently have to begin with up here. And then x gets simplified on the top and the bottom, and you are left with the integral of 1 over 2 root u du. Now we can't integrate that as it stands because you need it in index form. Well, the 1 over 2 for the half can stay there. The square root of u, though, is, if I bring it up to the top, u to the minus a half, which is where this comes from here. Now we can differentiate that. What am I on about? We can integrate that, rather. If you integrate this, well, first things first, you can take the half outside the integral. Now, a few of you made a few mistakes on your homework in my class when you tried to do that. You can only do that if the half is multiplied by everything underneath there. Well, because there's only a u there, it means I can take the half out. I'll just be left with u to the minus a half. Now, if I integrate that, raise the power by 1 to a half, divide by the new power of a half is same as times it by 2. Don't forget the plus c. The half and the 2 will cancel each other out, and you're left with u to the power of a half plus c. So that's what you get if you substitute all of this in, simplify as much as possible, and integrate. But you still have to substitute your u back in for your original substitution, which was 2 plus x squared. So it becomes 2 plus x, I think this should be squared there. 2 plus x squared to the power of a half, or you could write it in a different way. Okay. If you have any questions, please let me know. All right, this is supposed to be the point of these live lessons. If you have any questions, or if I'm going too quick or anything like that, let me know. I would suggest watching the video back again. I'm not going to take the full hour today, so just to get real grips of it, it might be a good idea to watch it back again straight afterwards, to be honest. There's 2 questions left to do. So this question here is to find the integral of x plus 3 times this whole bracket, which is cubed. Again, good news, they tell us the substitution in the question. U equals x squared plus 6x plus 4, essentially the inside of this bracket here. Now, if I substitute, well, my steps are, remember there was those steps from earlier. The first one is to differentiate your substitution. So if we differentiate u with respect to x, I end up with 2x plus 6. Now, Mr. Stratford has factorized this here. It might not immediately be obvious for you to factorize that, but it will hopefully when nothing immediately looks like it's going to cancel out later on. So you can either factorize it now or later on. So our second step is to get dx on its own. So remember, dx will swap places with 2x plus 6 in this case, or 2 brackets x plus 3. So these things here are original substitution. My dx equals, those 2 things need to be substituted in. That gets substituted in there. This gets substituted in there. Remember, this on the left here is my original question. I end up with this x plus 3 times u cubed, because all of this is u. Dx is replaced by du over this. Now, as you can see, by factorizing, x plus 3 and x plus 3 will cancel out. You are then left with u cubed over 2 du. So if I integrate that with respect to u, raise the power to 4, divide by 4, u to the power of 4 over 8 plus c. To finish my question, I need to substitute u back in, So it becomes all of this, which was u to the power of 4 over 8 plus c. Okay, last question. I think it's maybe there's two. I could leave that one for you, I guess. I'll see what time is now. So some examples involving trig. Trig substitutions, sometimes they may be a little bit more obvious, I think, if you have to choose for yourself. I don't know. But we don't have to choose for ourselves yet because they're still telling us in these questions. So example 3 wants me to find the integral of sine cubed x cos x using the substitution u equals sine x. Now, again, you might be thinking, can't I just do integration by parts for this? Because there's just two things multiplied together. You could if it was something a little bit easier than sine cubed x, though. We don't know how to integrate that or differentiate that. It's not the same as sine 3x. This essentially means sine x all cubed. So instead, I'm going to use the substitution u equals sine x, which we're told in the question. Our steps: differentiate sine x to give you cos x. Rearrange that to get dx on its own. Dx is equal to du over cos x. They swap places. Sub this in and this in to my formula, or my original question rather. Now this time, u is going to replace the sine x there, and dx is going to replace that dx there. Because it was sine x all cubed, that becomes u cubed, cos x. And now it's du over cos x at the end. Cos cancels. We're left with just the integral of u cubed du. To integrate that, raise the power by 1 to 4, divide by 4 plus c. Substitute u back in, you end up with sine to the power of 4x over 4 plus c. Maybe a bit more straightforward now. Hopefully you're getting grips with this as well, and it's not all appearing absolute nonsense yet, or still. Okay, so I will do this one because I think we have time. Example 4. Find the integral of sec squared tan x dx using the substitution u equals sec x. So our inverse trig functions are important here. Mr. Stratford wrote a little important note here that it's not a common derivative. So in other words, you don't need to memorize it. It's given in the formula booklet. So the differentiation of sec x is not one that you need to memorize. Anyway, if my substitution was u equals sec x, then first step is differentiate it. It is sec x tan x. Rearrange to get dx on its own. Dx equals du over sec x tan x. We end up with those two things. My original substitution, my dx equals, they're going to be substituted into my original equation in those two places there. So instead of sec squared, it's now u squared. Instead of dx, it's this du over sec x tan x. Okay, now we need to think, how do I simplify this? Now, there's a little trick with this one. Now, if you were, I think if you try to do this, I don't necessarily want to write over it because I don't know off the top of my head how to rub it out if I write over the top of it. But your immediate thought might be, well, can't I just do tan x cancelling out with tan x there? And then I'll be left with just 1 over sec x, which is potentially true, okay? But then you'll end up with u squared over tan x. Let's just write that. I'll tell you what, I'll write that up here. So your immediate thought might be, well, u squared, cancel the tans out. You'll have u squared du over sec x, which is true, okay? But then that's the same as this, u squared over sec x du, okay? But we don't know how to differentiate this, not differentiate, we don't know how to integrate this at all. However, sometimes a substitution that you used earlier might still be important, and I can put it in if it appears again. Remember, my original substitution was u equals sec x, which means I can sub u in for the bottom of this fraction. It's all with respect to u, so that's absolutely fine. So I end up with that. U's will cancel out in this. And you are just left with the integral of u to u, which is where this comes from here. Raise the power by 1, divide by 2, sub u in, which was sec x in the first place. So sometimes you might have to substitute one of these things, particularly the u, in more than once, in more than one place, if it makes your job a little bit easier, because you might reach this stage here with u squared over sec x and think, where on earth do I go from there? But remember, sec x was this in the first place. Or it might have some relationship with your original substitution. Okay, and that's it for today. Difficult topic. Okay, it is more difficult if you are not given the substitution, though, which is going to happen at some point. It might not happen in your end of year exam. It's going to happen at some point on a worksheet we're going to be doing in the next week. Okay, so unless you have any questions, guys, off you go. I'd suggest reading the notes or watching the video again.